Combinations is what we're going to look at. Now, this is when the actual order of the arrangement is not important. So permutation, order is important. Combination, the actual order, is not important. So it becomes a selection rather than an arrangement. What is the difference? So we're going to arrange them in a line, but this time the order is not important. In other words, AB, as far as we're concerned, is the same as BA. Might look different, but we don't care about the order. It's still the same letters. And let's work out some sort of pattern. So if there's 5 objects, but I only want to arrange 2 of them, because clearly if I arrange all of them and the order is not important, well, there's just one way of doing it. I just use them all. But I only use 2 of them. Here's all the possibilities if it was a permutation. And if it was a permutation, we'd say, well, 5p2, there are 20. But we have double counted a lot there, so let's cross those out. See, BA is the same as AB, CA is the same as AC, and so on. And what we're left with is those 20 divided by 2 factorial. So we end up with 10 different ones. So 2 factorial. What's the significance of that? Well, let's have a look if we arrange 3 of them. Whoa. Okay. So 5 objects, arrange 3 of them. If it was a permutation, 5p3, which is 60. Again, let's cross out the ones that are doubled up and in some cases tripled up. There's a few more of these. Here we go. So let's get rid of all those. What are we left with? Well, we're actually left with 10. 60 divided by 3 factorial. Hang on. When it was 2 objects, we divided by 2 factorial. When it was 3 objects, we divided by 3 factorial. So what we're actually doing is we're dividing by the number of ways we could have arranged the objects. Because those arrangements are not important, well then we just divide by those ways. So alright, if we have n different objects and we want to arrange k of them, don't care about the order, then it's the number of permutations, npk, divided by k factorial. Now as a formula it would become this. You may recall the permutations formula was n factorial and n minus k factorial, but we're now also dividing by k factorial. The nice thing about this formula is the 2 numbers on the bottom add up to give the number on the top. But there is also a button on our calculator for that. So nck, C for combinations obviously. Let's do this one. How many ways can 6 numbers be chosen from 45 numbers? It's a basis of a very popular gambling game that people play every week, that being Lotto. And the idea is you want to get the 6 numbers, same 6 numbers, you win a lot of money. The order of the numbers come out, not important. So there are 45 C6 ways of doing it. Turns out to be 8,145,060. So if you were incredibly patient and were willing to fill out 8,145,060 entries, you could guarantee you win Lotto. Now, I haven't played it for a very long time. I think it's about 70 cents a game. So it costs you about a bit over $5.5 million. But you would guarantee that you win. So the gamble no longer becomes, would you win? The gamble becomes, are you the only person that will win? Because the way Lotto wins is if 2 people do it, you split the money. So if it's one of those big jackpot ones that's 10 million, you think, oh yeah, I'll just put 5 million down, win 10 million. Brilliant. But if someone else also happens to win, you divide it by 2 and now you're losing money straight away. Of course, it does bring up the other question. If you've got $5 million to spend to cover every combination, why would you be betting on Lotto if you've already got $5 million? I mean, who needs to win Lotto if you've got $5 million? Committees of 5 people are to be obtained from a group of 7 men, 4 women. How many committees are possible? No restrictions. Well, if there's no restrictions, again, it doesn't matter that we're talking about men and women. We're just talking about 11 people. And we want to get 5 of them. So 11C5, there are 462 different committees we could form. What happens if we're back in the dark old ages, which used to happen, and they say, no, only men can go on this committee? Then we're only choosing from 7. So 7C5, and straight away we narrow it down to 21 committees. Well, then people became a bit more enlightened, and they said, tokenistically to start off with, oh well, we can have at least 1 woman on the committee. Well, this is where I use the complementary idea again, because why do more work than I have to? At least one, well, the complement to that must be what we've already worked out. The one with none of them, so if I go subtracting the ones with none of them from all the possibilities, I must be left with the ones that have at least one, 441. So we can still use this complementary idea like we saw in probability. Card games. A lot of card games, how you win are based on the probability of a particular hand happening. So you get a hand of 5 cards dealt from a regular pack of 52 cards. How many different hands could you get? Well, there's 52 cards. We're going to select 5 of them. There's actually quite a few different hands you could be dealt in this game. 2,598,960. What's the probability of getting 3 of a kind? Now, before you start panicking, you're never going to be asked a question like this in a test, because they can't assume knowledge. They can't assume you know the rules of these different games and things like that. If they wanted to ask you about it, they'd have to explain to you what 3 of a kind meant and things like that. 3 of a kind just means 3 cards with the same number on them. For those who are unfamiliar with cards, there are 13 different numbers. Well, there's 10 numbers and then there's Jack, Queen, King. There's 13 different things you could have. We're saying we want one of those numbers to turn up 3 times. So the first thing I'm doing is I'm choosing which number would be 3 of a kind, 13C1. But now I'm saying I want 3 of them. There's 4 different suits in a pack of cards. So of the 4, I want 3 of them. So it might be the number 2 we've decided we want. So there's a 2 of hearts, 2 of diamonds, 2 of clubs, 2 of spades. I just want 3 of those. So of the 4, I'm going to get 3. So 4C3. But I still need 2 more cards. So of the 48 remaining cards, I'm going to choose 2. Now you might be thinking, hang on, whoa, 48? Surely there's 49. We've only taken 3 out. It's a pack of 52. But yeah, I don't want to get the other, if it was the number 2, I don't want the other number 2. Because if I got the other number 2, I don't have 3 of a kind, I have 4 of a kind. So I'm excluding that one. So 48C2, 58,656 different ways I could be dealt 3 of a kind. In fact, the whole rules of the game poker, some of you might be familiar with poker, who wins, who loses is based on the probability of getting that hand. So 3 of a kind, it's not a bad hand. If we wanted to work it out, there's our probability. Sometimes it makes more sense to think of these as percentages when these numbers are getting so large. It's about a 3.2% chance of getting that. Alright, let's look at the actual HSC one. 2004. We've got a 4-person team. It's going to be chosen at random from 9 women, 7 men. How many ways can this team be chosen? Okay. Well, like the one we saw before, it doesn't matter that we got men and women, we just got 16 people. So 16C4, 1,820. What's the probability that the team will consist of 4 women? Now it's a team of 4, so in other words, they're all going to be women in this team. So from the 9, I'm going to choose 4. 9C4, which is 126, but we want the probability. So it'll be 126 out of those 1,820. 9 in 130 is our probability. A little bit about when we divide into groups. So dividing objects into groups. We're going to divide a group of m plus n objects. We've got m plus n objects. We're going to divide them into 2 groups. One group m objects, one group n objects. So how do we split it into these 2 groups? If I work through it, I can actually make it easier for myself. Now technically it's this. M plus n is how many we have altogether. I want to choose m of them. So I get m plus ncm. Now if I put that in the factorial notation, it would be this. M plus n factorial on m factorial n factorial. But that idea now helps me when I think of different problems. Because imagine I have this. Imagine I have a group of 2 m objects and I'm going to divide into 2 groups, each of them containing m objects. In this one I have to be careful. Because using that idea, sure it's 2mcm, But I'm going to have to divide by 2 factorial, the number of ways I could arrange the groups. And here's why. I need even groups. 1, 2, 3, 4. Now you've got 5. Ah, good. 2 tables here. We've got 5 on this table, 5 on this table. So let's imagine I've got 10 people and I want to divide them into 2 groups of 5. So I choose my first group and I end up with this group over here. Here's my first group. And this automatically becomes the other group. So that's one way I could have done it. But another way I could have done it is I could have chosen these 5 first. And then they automatically become the other group. But I've ended up with the same groups. So the actual order that I selected the groups, whether I chose this group first or whether I chose this group first, doesn't matter. So I divide by the number of ways those 2 groups could have been arranged. Now in the first one, I didn't have to do that because they were different size groups. So let's say, here's the 2 groups. I've got a group of 4 and a group of 3. So I choose the group of 4 first. Automatically this becomes the other 3. But I now can't reverse that, because if I choose the group of 4 first, well, I can't end up with this group because they're a group of 3. So it's only when you've got the same number in the groups that I have to divide by the number of ways I could arrange the groups. So divide by the number of ways the groups of the same size can be arranged. So we would end up with something like that. Okay, well, let's take it a step further. If I've got a group of m plus n plus p objects and I'm going to divide them into, well, it says 2 there, but it's 3 groups. Divide them into 3 groups that has m, n and p. Okay, what happens? Well, I've got m plus n plus p that I'm going to choose from. I'm going to choose m. There's my first group, done. Now I'm going to get my second group. My second group, I'm now left with n plus p people, and I'm going to choose n of them. There's my second group, automatically creates the third group. But look what happens when we put it in the factorial notation. This n plus p factorial ends up cancelling, and I end up with something very similar to the one before. It's simply the total number of arrangements goes on top, but then I just divide by the size of each of the groups, factorial. So let's now do this. 15 students, and I'm going to divide them into 3 equal groups. So now that we know this information, this becomes very quick. There's my answer, done. Okay. 15 students all up, 15 factorial. I'm creating 3 groups of 5, so I've got 5 factorial, 5 factorial, 5 factorial, because I've got 3 groups of 5. But hang on, the number of ways the groups of the same size can be arranged, well, there's 3 groups of the same size, so I'll also divide by 3 factorial. And we get, oh, isn't that a nice number? 126, 126. There we go. All right. A restaurant has 3 tables. Each of the tables has 4 seats. 12 people arrive for dinner. How many ways can they be assigned to the tables? 12 factorial, there's 12 people. 4 are going on 1, so basically I'm putting them into 3 groups of 4. 4 factorial, 4 factorial. Hang on, groups of the same size, so 3 factorial. But there is a difference, because remember, can be assigned to the tables. So now the arrangement becomes important, because let's say these are the 3 tables that you're going to sit at for dinner. Putting this group on this table is different to putting them on this table, is different to putting them on this table. So now I have to multiply by 3 factorial the number of ways the tables, if you like, could be arranged. But hang on, all that really means is we cancel out the 3 factorials. So really, all I have to worry about is the 4 factorial, 4 factorial, 4 factorial. So the question I have to ask myself, when I put them into groups, am I doing anything with the groups? If all I want is these other groups, then all right, I divide by the number of ways that could be arranged. If I'm going to go and do something with the groups, like allocate them jerseys if it's a sporting team or something like that, then the order becomes important that I selected them, so I don't divide by, in this case, the 3 factorial. So if the groups are going to be arranged, you don't divide by the number of arrangements. A permutation, so what we've been looking at in the past few days is really the same as this. A permutation is a combination multiplied by the number of ways the objects can be arranged. So some people, when they're looking at these questions, solve it by going, I'm going to select, then I'm going to arrange. I'll select the people, then I'll arrange the people. So they do the combination first, then multiply it by the arrangements, turn it into a permutation. And it can be a useful way of thinking about some problems. Alright, I now just want to show you some techniques that can help. First one here is what we call the insertion method. Now this is useful when you've got a problem when you say some of these objects are not allowed to be together. Not allowed to be together. And here's a typical sort of one. The letters of the word between are arranged in a line. In fact, I think this might have even come from our textbook, I'm not sure. In how many ways can they be arranged if all the E's are separated? So the E's are not allowed to be together. So what we would have done is said, well, okay, let's look after the restriction first. The restriction is the E's have to be separated. How many ways can I do that? Now, I usually do something like this. I put a dash for each one and then actually work out. And I'll go, well, look, yeah, it is possible I could put the 3 E's like that. But actually, this last E, it could go there, or it could go there as well. So I've actually ended up with 3 different ones there if the first 2 E's are in this position. But I could have put the first 2 E's in this position, which means the last E could go there, or it could go there. There's 2 different ways. But hang on a sec. I could have put the first 2 E's like this. Now there's only one place I can put the last E. So that's 1. But that's assuming that the first E goes in the first position. So if I put the first E in the second position, I can go through the same idea. And I get 2 and then 1. But hang on, is it possible I could put the first E in the third position? Yes, I could end up with that one. I think that about covers it. So there are 10 different ways we can place the E's. So we've done that. Now we'll multiply it by the number of ways we can arrange the other letters, 4 factorial 240. That's probably the traditional way of doing it. The insertion method allows us to do it a lot quicker. Right? It actually is the reverse way of thinking about it. With actually, I'm going to arrange the unrestricted objects first. So the unrestricted objects are B, T, W and N. Let's assume they fell into that position. And you'll notice I put a gap between the letters. So what I'm saying is there's 4 factorial ways of arranging the B, T, W and N. But it now creates spaces to put the other letters. There are 5 spaces. But because the E's have to be separated, then I can only put an E in one of those slots. I can't put 2 E's in the one slot. So now I just have to choose, so it becomes a combination, choose which of those slots I'm going to use. So of those 5 slots, I'm going to choose 3 of them. 240. There's my answer straight away. Okay, that's what we call the insertion method. What about if exactly 2 of the E's are together? I can still use this idea because it'll be 4 factorial. I'll do the B, T, W, N. Exactly 2 of the E's are together. Well, hang on. This time the order is important because double E, I now think of double E as one letter. Double E is different to single E. I'm now going to choose 5 of these spaces to put these 2 letters in, but the order is important, so it becomes a permutation rather than a combination. So I'll multiply it by 5p2, 480. All right, final idea. Using separators. And this is really good when you have to divide really big groups into smaller groups. Here's a question. 3 pirates are sharing out the contents of a treasure chest, and containing 48 gold coins, and there's 2 lead coins. So you've got 48 gold coins, 2 lead coins. So the first pirate comes along and takes coins out one at a time until he pulls out a lead coin, and that's when he stops. That's how much treasure the first pirate is allowed. Then the second pirate comes along and starts taking out coins, as many as he can take out, until he hits the other lead coin. And that's how many coins he can have. And then the last pirate gets whatever's left. How many ways can we distribute these coins then? So we've got these 48 coins we have to distribute amongst the 3 pirates. We can now change the question. Instead of being coins, let's imagine they're letters. And I'm going to arrange 2 L's, the lead coins, and 48 G's, the gold coins. The L's are going to act like the separators between the different treasure chests. So it's like now saying, how many words can you form using 48 G's and 2 L's? Well, we know that problem. We saw it yesterday. 50 factorial, number of letters we have, divided by 48 factorial for the gold ones, 2 factorial for the lead ones, 1,225. You see, and you'll notice it says extension 2 here. In 2012, they had this question in extension 2. In how many ways can 10 identical coins be allocated to 4 different boxes? Okay, same idea. This time though, I don't have the lead coins, so I'm going to call them just separators. There's some separator that will stop when one person finishes and so on. So there's 4 different boxes. Once I've filled up the first box, bang, pull out the separator, now start on the next box. Pull out a separator, now start on the next box. So I can change this question to be, how many ways can 3 S's and 10 C's, so 3 for the separators, 10 for the coins, be arranged? There's the answer. 13 factorial and 3 factorial, 10 factorial, 286. But the real interesting question about this, only 1%, this was extension 2 by the way, only 1% of the states got that question correct. Yeah? And you see how quick it is if you use this idea. A hostel has 4 vacant rooms. Each room can accommodate a maximum of 4 people. How many ways can 6 people be accommodated in the 4 rooms? If there were no restrictions, then it's the basic counting idea. We go back to that. Because the first person comes along and has a choice of 4 rooms. Then the next person comes, a choice of 6 rooms I should say. The first person comes along, has a choice of 4 rooms. The second person comes along, has a choice of 4 rooms. And so it's a 4 times 4 times 4, power of 6. That's if there's no restrictions. But let's take away if there's 6 in a room, because we're not allowed 6 in a room. So let's take away all the possibilities that there's 6 in a room. How many ways are that? Well, the first thing we've got to decide is, well, which room is going to have 6 people in it? There's 4 rooms, going to choose one of them. So there's 4 ways of doing it. But what about if there's 5 in a room? We're not allowed that either. So we're going to choose which room has 5 in it, 4C1. But then we have to choose which 5 people are going in that room. So of the 6, we'll choose 5. Then that will leave us one person who has to choose one of the other 3 rooms, 3C1. 72 ways of doing that. Take away all the possibilities, 4,020. 15% of the state got that right. That's the one that was multiple choice. Think about it. If you did random guessing, what percentage would you expect get correct? There's 4 options, 25%. 15% got it right. It's telling us, hey, they should have just guessed. And they got a better chance of getting the right answer than trying to work this problem out. It was hard, of course it's hard, it's extension 2. 14E, that's enough from me.